Okay, here's our next example here. We want to determine the intersection of these three planes. So we'll call them again plane 1, plane 2, plane 3. We want to start by checking out our normals here. So just say our normal to the first one is 1, -3, -2. Our second normal is going to be 1, 11, 5. Our third normal is 2, 8, 3. So, look at our normals. We ask ourselves, are any of these planes parallel? And what do we see just by looking at them here? Are any of our planes parallel? Brody says no. So no planes parallel. Next thing we could check is we could check to see if any of our normals were coplanar. So we can do the triple scalar product again. N1 cross N2 dotted with N3. This is all step 1. We do all that, and it works out to be 0 in this case. So now this tells us that our three normals are coplanar. No planes are parallel, but the normals are coplanar. So now we've got two possibilities here. These things could intersect in a line. Let's just say possibilities. It's possible that they intersect in a line, or that we have that situation where they form that little triangular prism. Okay, and we don't know which one we have here. So all we can do at this point is we can start trying to solve for our solution, which the only one that is consistent is the one where we have a single line that is our line of intersection. So we're going to try to find the equation of that line and see if we get something that makes sense. If we get something that is mathematically inconsistent, we're going to know that we have this case down here where there is no solution. So this one is consistent. It has a solution. This one is inconsistent. So it'll give us something that is inconsistent when we try to solve it. And of course, I still can't spell the word consistent. Consistent. Okay, so let's start trying to solve this thing. Our first step is going to be the same as step before. We're going to eliminate one of our variables from two of our equations. I think the easiest thing to do is to eliminate x from 1, 2. So from plane 1 and plane 2. And we're going to do that just by subtracting them. So if I do plane 1 minus plane 2, let's see what I get here. I get the x's go away. I get negative 14y minus 7z and 4 equals 14. Okay, just subtracting those two. So I've eliminated x from two of my equations. I'm going to pick a different two and eliminate x from them as well. So let's say step 3. Eliminate x from, which ones are we going to pick here? I'm going to pick the ones that I did in my notes here. So I'm going to do 2 and 3. Okay, so plane 2 and plane 3. This is a little bit trickier. I'm going to have to multiply each of these. No, I'm going to have to multiply plane 2 by 2 to get these things to eliminate. So I'm going to do 2 times plane 2 and then plane 3 here. So let's just write out what that is going to be. 2 times plane 2 is going to be 2x plus 22y plus 10z equals negative 10. And then plane 3 will just keep the same, 2x plus 8y plus 3z equals 4. And we're going to subtract these two equations, and that's going to eliminate our x's again. So 22 minus 8 is 14, so 14y. 10 minus 3 is 7z. And negative 10 minus 4 is negative 14. Okay. Now, our next step after doing this was to take these two equations that we had gotten for y and z and use them to solve for the values of y and z. Let's take a look at these two equations that we've got here. Up here, if we divide everything by negative 7, we get 2y plus z equals negative 2. We'll call that one equation 4. If we divide everything down here by, the equation down here by 7, so we simplify this, we get 2y plus z equals negative 2. We'll call that equation 5. Equation 4 and equation 5 are exactly the same. So what's going to happen when we try to solve this system of equation 4 and equation 5 for values of y and z? Well, you may know the answer, but let's just take a look at it. Let's write 4 and 5 out here. So this is 4, this is 5. We've got the same thing here. They're both 2y plus z equals negative 2. 2y plus z equals negative 2. We can subtract the two of them, and we end up with 0 plus 0 equals 0. Okay? Now we have to ask ourselves, for what values of y and z is this expression true? Well, any value of y and z is going to satisfy this because, 0 always equals 0. So this is always true. This is telling us that we have an infinite number of solutions. Okay? So at this point, we know which of these two cases we have. Okay? Up at the beginning, we couldn't decide whether these things intersected in a line or intersected forming this little triangular prism. Well, if we have an infinite number of solutions, that means these things have to intersect in a line. So now we want to switch gears a little bit, and we want to find the parametric equation of this line. Okay, so 5, let's move this down a little bit. So I'm just going to draw attention to the fact that these two are the same. Okay? And we'll move on down here and try to find 5, find the parametric equation of the line of intersection. Now, the way we're going to do this is going to be similar to what we did when we were doing the intersection of two planes. Okay? We're going to start from what we have for equation 4, which is 2y plus z equals negative 2. And remember, when we're looking for a parametric equation, let me just fix this, intersection. When we're looking for a parametric equation, what we want are expressions for x, y, and z. Okay? X equals something, y equals something, y equals something, z equals something in terms of the parameter t. Let's use this to get an expression for z. So let's rearrange this here. We'll get z equals -2 plus 2y. So we've got our expression for z. What did I do wrong there? Sorry? Minus 2y? Is it still -2? Okay. Minus 2y. Okay? So we've got our expression for z. We're done with z. So the next thing we want to do is eliminate z from the system. So we can pick two of our planes and eliminate z. So I'm going to pick plane 1 and plane 3. Because if I do 3 times plane 1 and 2 times plane 3, I can eliminate z fairly nicely. So I'll get 3x minus 9y minus 6z is 27. And 4x plus 16y plus 6z equals 8. And then I just need to add these two things together. Now, I didn't have to pick plane 1 and plane 3. I could have picked plane 2 and plane 3, or plane 1 and 2. I think I chose 1 and 3 here because I had already used, if I go way back up here, I'd already used 1 and 2 and 2 and 3. So I chose 1 and 3 this time. But I don't think it really matters. So we want to add these two together. We'll end up with 7x plus 7y, our z's go away, equals 35. And what we have right here is we have an expression for z in terms of y. So let's use this thing we have here to get an expression for x in terms of y. So 7x will equal 35 minus 7y. Divide through by the 7. 5 minus y. Okay. So we've got expressions for z, x, we just need something for y. So we can just choose y equals t. And our parametric equations will become x equals 5 minus t, y equals t, and z equals -2 minus 2t. And that's the equation of our line of intersection. So what can we say now? We found the equation, so we can say something like, therefore, the system is consistent, because there is a solution. It's dependent, because we have an infinite number of solutions. And we now have the equation of our line of intersection. Line of intersection is, and let's just put this into vector form, we're going to have 5, 0, -2 plus t times -1, 1, -2. And there we are. So the last example that we're going to do here, again, we've got our three planes, plane 1, plane 2, plane 3. First step, we'll take a look at our normals. Our normals are going to be 1, 1, negative 1, 2, 2, negative 4, and 1, 1, negative 2. Now, first thing we do is we look at the normals to see if anything is parallel. And what we notice is that normal 2 is a scalar multiple of normal 3. So these two guys are parallel. Now, is plane 2 just parallel to plane 3, or are they parallel and coincident? Well, let's see. We can take a look at the equations here, and we see that if I take plane 3 and multiply it by 2, each term by 2, I get plane 2 coming back. So plane 2 is a scalar multiple of plane 3. So that's telling us that not only are these two things parallel, they are coincident as well. So we've got two planes that are parallel and coincident, and a third one coming along. We know then that we are going to have a line of intersection. Okay? These have to intersect in a line. So what we want to do here is, let's say, I'll just say a line of intersection. Therefore, a line of intersection. Okay? Now, because plane 2 and plane 3 are essentially the same plane, Brody. It's like you're doing, exactly, you're doing the intersection of two planes. I can take whichever planes are easiest to work with, and I think 1 and 3 are the easy ones to work with, and we just find the line of intersection of plane 1 and plane 3 is our solution. Okay? And we've done these questions where we're looking for the intersection of two planes. So what are we going to do here? We are going to eliminate x from 1 and 3. So if I just do plane 1 minus plane 3, that'll eliminate x for me, and that'll get me x minus x. X's go away. Y minus y. The y's go away. Negative z minus 2z gets me z. And then 5 minus 3 gets me 2. So this simplified a lot. I ended up with just z equals 2. Now remember, what I'm going for here is I'm going for parametric equations. So I want expressions for x, y, and z. I've got my expression for z. Okay? So now I want to get rid of z back in one of my original equations. This is going to be really easy to get rid of z because I can get rid of z simply by substitution here. So I'll just say eliminate z from, and which one am I going to do here? From plane 1 by substitution. Okay? Usually you had to do elimination to get rid of the variables, but because this is just a number here, I'm just going to sub it in. So I'm going to get x plus y minus 2 equals 5. Okay, this is from plane 1. And what I'm going for, remember, are expressions for x, y, and z. So let's get an expression for x here. It doesn't really matter which way I go. So I'll get x equals, I add the 2 on that side, 7 minus y. So now I have expressions for z, an expression for x. All I need is something for y. What am I going to pick for y if I'm going after parametric equations here? What can y be? Yeah, y can be my parameter. So we're going to choose y equals t, and we'll go from here. We'll have x equals 7 minus t, y equals t, and z equals 2 is our parametric equation. So we can wrap this whole thing up pretty quickly here. Therefore, the system is consistent because we have a solution, this line. It is dependent because the solution is a line, infinite number of points of intersection here. System is consistent and independent. And let's just say the line of intersection is, and let's put this in vector form, is going to be 7, 0, 2 is our point, plus t times negative 1, 1, and 0. Okay, and there we are. We've classified the system as consistent and dependent, and because it's consistent, we have found the solution here.